We are now going to go over a more formal proof of the fundamental theorem of calculus. So just to remind you what we're trying to prove, the fundamental theorem of calculus states that if our function f is continuous on a closed interval, then the function defined by integrating that function from a to x for an x that is between a and b, this is a differentiable function on the open interval ab, and its derivative is exactly the value of the function f inside the integral at x, where x is the upper bound of integration. So to show that, we're going to take an x and x plus h that are both in the interval ab. If x is in the open interval ab and h is sufficiently small, we can make sure that x plus h is in the interval ab. H can be positive or negative. When we take the difference g of x plus h minus g of x, this is something we consider because the derivative of g at x is going to be the limit of this expression divided by h when h goes to 0. So this difference g of x plus h minus g of x is just a difference of the corresponding integrals of f. And we're going to split this integral in two parts. We have seen that if we integrate from a to another point, b, say, it's the same as integrating from a to c and then from c to b. So we can split that into the integral from a to x plus the integral from x to x plus h. And under that form, you see that you have the integral of the function f from a to x, and then it is subtracted in the last term. So what remains is simply the integral from x to x plus h of the function f. What we're interested in is the quotient of this expression by h, because this is what is going to define the derivative. So if we divide by h, by a non-zero h, we obtain 1 over h multiplied by this integral from x to x plus h. And now we're going to try to figure out what is the behavior when h goes to 0, because if g prime of x exists, it is the limit of this difference quotient when h goes to 0. So, because the function f is continuous on the closed interval from x to x plus h, it means it reaches its maximum and its minimum on that interval by the extreme value theorem. And therefore, there are two values, u and v, in that interval from x to x plus h, where the function takes, respectively, its minimum value and maximum value. And we're going to denote by little m, the minimum value, and by capital M, the maximum value. Of course, an f is always between little m and capital M on the interval from x to x plus h, so one of the properties of the integrals that we have seen is that in that case the integral of the function from x to x plus h is going to be between this minimal value multiplied by the width of the interval, which is h, and this maximal value multiplied by the width of the interval, which is h. Here we're assuming that h is positive, but this is only for the sake of argument, and if it is, little m is just f of u, capital M is f of v, and if h is positive, we divide by h and we obtain that this expression 1 over h multiplied by the integral from x to x plus h of the function f is between f of u and f of v. But this expression 1 over h multiplied by the integral from x to x plus h is simply the difference quotient g of x plus h minus g of x over h. So what we obtain is that this expression is between f of u and f of v. Of course, you may say, well, we assume that h is positive, but h doesn't need to be. If h was negative, we would just get f of v on the left-hand side and f of u on the right-hand side. So now what happens if h goes to 0? Well, u and v, by definition, are points that are in the interval from x to x plus h, and on which the function takes the minimal and maximum value. And the function f is continuous, so if h goes to 0, u and v are in the interval from x to x plus h, so if h goes to 0, u goes to x and v goes to x. So f of u as h goes to 0 is approaching f of x because f is continuous. So if u is approaching x, f of u is approaching f of x. And similarly, v is approaching x, and therefore f of v is approaching f of x by continuity of f. So we have the same limit f of x on the left-hand side and on the right-hand side, and using the squeeze theorem, the function that is in between has necessarily the same limit as h goes to 0, which is f of x. But since the limit exists, it is the derivative of the function g, and this derivative is f of x. So we have proved the fundamental theorem of calculus. Now that we have a proof, and you have seen some examples on how to use the fundamental theorem of calculus in the 2 previous videos, you can turn to your homework on this section.